So one of the ways that we can reduce esters is with an LAH reduction. LAH, or lithium aluminum hydride, is a strong reductant of esters and will reduce pretty much any carbonyl. Now, when it comes to esters, we generally have to use LAH. Sodium borohydride, which you may be familiar with from reducing aldehydes or ketones, in general is not a strong enough reductant to reduce esters. But LAH, with the larger electronegativity difference between lithium and aluminum, more reactive, and is able to perform these reductions. Now, the mechanism we're going to show is most likely an oversimplification of this reaction, but for the purposes of a sophomore, junior level organic chemistry class, it works fine to illustrate what we need to know about this reaction. So we're going to show the active species as H-. We put that in quotes because it's definitely not H-. There's no free H- in solution from LAH. But LAH is reactive enough that it behaves pretty much like H- would. And we can put pretty much any R groups we want on our ester. And that H-, very strong nucleophile, carbonyl, we know is a good electrophile. And this reaction happens extremely quickly. H- attacks the carbonyl, we shift our electrons up onto oxygen. Unlike a lot of reactions, we largely show this as going in one direction because to be reversible, we'd have to kick H- out, and we know that's pretty much about as bad of a leaving group as you're going to come up with. From here, O- can add its electrons back in, kick out the leaving group, and we form an aldehyde. But the reaction's not done. Why not? Well, hopefully we know at this point that aldehydes are more reactive than esters. And so if we're adding a substance in, as we have with LAH for this reaction, and if it's reacting with an ester, and now we've made something that's even more reactive, an aldehyde, we know the LAH will definitely react with an aldehyde. In fact, the aldehyde is one of those functional groups that we don't even, in theory, need LAH for. The weaker reducing agent, sodium borohydride, is strong enough to reduce lithium, the aldehyde. So the fact that we've got an even stronger reductant here in LAH, that aldehyde's going to immediately get reduced. Again, for our purposes, this is going to be good enough. We'll show it as H- in quotes. It adds into the aldehyde. Electrons shift up onto oxygen. We form our anion, which then we quench, typically just with water. But if you're actually doing this reaction, you want to be very, very careful and quench it slowly, usually at low temperature. but that'll protonate our alcohol to give us our final product. So the result here, if you take pretty much any ester and have it react with LAH, you're going to get two reductions. You're going to end up at the alcohol. It doesn't matter how complicated that piece is on the other side of the oxygen, because it's just going to get lost in this reaction. Again, the first step is going to result in loss of your ester group, forming an aldehyde, and then it gets reduced a second time to form the alcohol. Now you might be wondering, is it possible to ever stop halfway? Can you stop at the aldehyde? And in general, if you're using LAH, the answer is no. There are other reducing agents, and you can look this up. I have another video, because these videos are just by reaction. If you do a dibol reduction of ester, in that case, under the right conditions, you can stop at the aldehyde.